My name is Pranav K. Raju, and I'll be presenting my lab report for the first lab, which is constant velocity. The purpose of this lab is to observe the motion of an object that is moving at a constant speed without changing direction. We do this by capturing a video of the motion, then analyzing the video using the tracker software to extract the object's position and corresponding times. In this lab, we use a marker as the object of observation. Throughout this lab, we are directly applying Newton's second law of motion, or the momentum principle. Newton's second law of motion states that the rate of change in momentum is equal to the vectorial sum of forces on a body. The first equation you can see here is derived from Newton's second law of motion, while the second and third equations are essential to this lab. The second equation, position update, is final position equal to initial position plus average velocity multiplied by change in time, and the third equation, velocity update, is final velocity equal to initial velocity plus net force divided by mass multiplied by change in time. Here is a preview of the two position versus time graphs I obtained after completing the steps of the lab. The first graph is the position versus time graph obtained from the tracker software, while the second graph is obtained through the CloseScript program. The procedure of this lab is, first, we recorded a video of a marker rolling across a table for use in the tracker software. Then, using the tracker software, I tracked the position of the ball frame by frame in an interval. Third, I got the data from Tracker and imported it into an Excel file, where I obtained the distance versus time graph. And finally, using the starter code provided, I created a model of the position versus time graph using data I obtained from the Tracker software. Here you can see on the left is the video of the marker we use in the Tracker software. Unfortunately, while trying to access the Tracker file again, I was unable to load the file properly, and therefore only the markings are visible. I apologize for that. But anyways, through the center of mass markings, we were able to determine the position of the marker at various points of time, and the velocity was determined to be 0.0576 meters per second. Then, we moved on to CloseScript, where we utilized the starter code provided and modified some of the values as seen in the images of the code below. After that, this was the position versus time graph that was obtained. Here is a comparison of the two graphs obtained in this lab. Here we can see that the graph obtained through CloseScript is higher than that obtained through the tracker software. Now, we will move on to sources of error, which may explain the results from the previous slide. First, when launching the marker, an initial force caused it to accelerate briefly, resulting in non-constant velocity in the beginning and giving us somewhat different results than the predicted model. There are also various other external forces at play, such as friction, air resistance, etc., which also makes it deviate from the predicted model. What if axes were flipped, that is, plus x and minus x were interchanged? If we were to flip the axes such that plus x and minus x are interchanged, the only change that would occur is that the slope is non-negative. Is it possible for you to say how many pushes and pulls are being added together to give zero net force in the case that you observed? No, it is not possible to determine how many pushes and pulls are being added together to give zero net force, as there are various forces at play such as friction, air resistance, etc. The computational prediction is based on constant velocity, which is not achievable by us under regular circumstances.